Okay, I just started recording. So I'm going to record all the meetings because I know some of you are in different countries, different time zones, so you might not be able to attend the live meeting. So I'm recording all the meetings. I'm going to upload them both on Blackboard and also on YouTube, so we can watch the videos later. So it's not mandatory to attend the class. That's the first thing. You can watch the videos. The second thing I want to talk about is that I think, if I understand correctly, we are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 days. And each day we are going to have 2 meetings, one from 9 to 11:05 and from 11:20 to 1:25. So we are, well, we are going to almost have around, I think, 20 meetings, something like that. And it's not, definitely it's not enough for this course. It's quite actually hard course. So we might not be able to actually cover all the topics of the book because I prefer you to learn better rather than just covering all the material. So we might not be able to cover everything. That's usually happens during the summer. Now, this semester, we have an additional difficulty that the course is online. If you look at the page I sent you, my homepage, I have a kind of detailed schedule. That would be our goal, but we might not be able to follow that completely. So let's see what will happen. That's one thing. The other thing is about the exams. I personally prefer take-home exam. I really don't like proctoring online. It's not really nice actually, because of difficulty online, which happened previous semester. Like there was the exam where proctoring and someone, well, proctoring online means, if you are not familiar with that, I guess you are by now, but if you're not, it means you would take the exam in your home, in your room, but you should turn on your webcam and we here should monitor you. And well, suppose you get disconnected suddenly, right? Your webcam goes off or whatever. And then, of course, I trust you. I wouldn't say if a person, if you get disconnected, it means someone is cheating. I don't like that. But then what's the point of proctoring? You know, it really doesn't make sense. So I personally prefer take home. I really trust you. I would just give you some questions. I would ask you to think about them for a few days and write down the answers, whatever you think are the correct answers, and send them back to me. But apparently some departments, some universities, some schools, some advisors, they're not happy with take-home exams. So I asked you, I'm repeating it here, please ask your advisor, if you have an advisor, or ask your department to make sure they're okay with take-home exams. If that's the case, we would have take-home exams. If not, we would go back to proctoring online. But in any case, I just want to tell you that I personally don't care much about the exam or those kind of things. I really want to see you trying, and I really like to see you, I want to feel your learning. And I promise you would get a good grade if I feel you're trying, even if you don't have very strong background. So for me, I would kind of compare you with yourself. I think we even have high school students. So I'm not gonna, this is a hard course, but I'm not going to compare you with the standard syllabus. I'm not going to say you should know the proof of this theorem, you should be able to do these long computations. I prefer to see you are trying, you're learning. That would be more important to me. And you are going to have a lot of chances during the semester to get a good grade. So don't be afraid about that. Just focus on learning. Don't think about grades at all. I just want you to think about learning. You're like spending your time. Time is like money, right? You're spending your time. So I hope you would learn some math. It's both fun and also it's useful. I promise it's math is useful in a lot of ways if you know it, right? So, and also we are going to have homework. So every day on Tuesdays and Thursdays when I'm teaching, after the class, I'm going to upload some notes on Blackboard. At the end, there are some exercises from the reference, the book by Larson, I guess. Yes. And Edwards, the multivariable calculus. The point is that I know because this semester it's a little hard to go out and it might not be easy for you to get the book. You might find the book online or whatever. I don't care which version you have, but because I've already in my notes, I'm telling you, for example, exercise 1, 2, 3, 4, 5 from the book. In different versions, these exercises are different. So it's okay, you can use your own version, but please, in the beginning of the exercises, write down that I am using like edition 11 or 10, or I have this version. So I know which book I should use to grade your homework, okay? That would be very helpful for me. Yeah, I think that's it. Is there any question? You can unmute yourself, or you can even open your webcam, camera, you can say whatever you want to say. Is there any question, any comment? Actually, I like to hear you speaking because I have no idea if you're following or not when the class is online, unlike the real classroom.
I have 2 questions.
Yeah.
My first one is, what edition do you prefer for the book?
Well, of course, the latest edition, which I think it's 11, okay. If I'm right. Let me check which edition. Yeah, 11. But 9th, 10th, and 11th are good. Before that, it has major like differences. But if also, I think you can find the book online. I think I'm not supposed to say that, but you can also find the book online and it would be okay. But the last version, of course, has the least amount of like typos and mistakes, and that's the 11th edition.
Okay, and my other question is, I know that the final's on the last day of class, if I'm not mistaken, but is there going to be a midterm? And if so, like what day is it going to be on?
Yeah, thank you for reminding me. I decide about the midterm, but as I said, we still don't know if it's going to be take home or not. If it's take home, there isn't going to be one specific day. I would give you maybe 4 days, and you would think at home, and then you would solve them, and then you would upload them on Blackboard. But if we decide to have online proctored midterm, we should fix one specific date, and that's another additional difficulty because some of you are right now in Korea, some of you are in Japan. I have some students now in Germany, and most of you are here in the US. So finding a time which is good for all of us might be a little challenging. We probably would decide, so because some of you are not even attending the class online, some of you are watching the recorded videos later. So yeah, if we want to have an online proctored midterm, we should decide and fix a time, which it would be during one of the classes, but let's see if we can have a take-home exam or not. We would decide.
So if there was, sorry, if there was a take-home exam, like what week would it be?
Ah,
do you know, or like, is that okay?
Yeah. So Yeah, let me look at my calendar. I think it's going to be almost at the end of this month, at the end of July. Yeah, like maybe the last 4 days of July, I guess.
Okay, thank you.
Yeah. Okay, and if it's not, if it's online, that would be also the case. It would be probably would be the last day of July. Yeah, I think that would be the case. Yeah, but don't be afraid. Even if you're not able to attend the online exam, I might be able to find another time for specific people who have for any reason they can't attend that specific dates. So it would be fine. There is nothing to worry about. Any other question? Okay, so we can start. If you have a question, you can just, at any point, you can ask me. Okay, so, okay, oh, do I have a question here? Do we take attendance? No, attending the class is not mandatory. As I said, some of you might prefer to watch the online videos, but I would recommend you to attend the classes and ask questions. And let's try, well, I like to make it as much as possible. I want to make it just like a real class, if it's possible. Oh, also, I have office hours and MLC hours. It means I'm available through Zoom at certain hours. You can look at, I would upload that on Blackboard. You can just, at those hours, we can Skype or we can talk through Zoom. If you have any questions, there are certain hours that we can discuss them and I can help you to resolve them. Because it is going to be a hard course, although I said I'm just, and as I said, I just want to feel you are trying and you're learning. So maybe office hours and MLC hours are a good time for that too. Okay, so let's start. Okay, let me share the whiteboard. Okay. Okay, the first chapter, which is chapter 11 actually, is vectors and the geometry of space. Okay, so multivariable calculus, which we are talking about and is the topic of this course, simply means math in higher dimensions. So the keyword here is dimension. What does dimension mean? So we have a feeling that the world, if you look at the world around you, if you look at your room, you have a feeling that you're living inside a three-dimensional space. So if this is you and this is your desk, okay, the heights are not correct, but it might give you the feeling that the world we are living in, it is three-dimensional, right? So you can go, what does that mean? It means you can go to right, you can go to left. Let's call that y-axis. There is another axis you can walk on that. You can come forward or you can go backwards. Let's call that x-axis. You can jump or you can sit down. Let's call that Z axis. So there are, in some sense, 3 independent directions. That's why we call it 3-dimensional world. But for example, suppose we have a piece of paper. Suppose this is a piece of paper. Okay, this is a sheet, a piece of paper. And suppose we have a point in this piece of paper. There are 2 independent directions. The point can go, it can go to right, it can go to left, it can go up, it can go down, but it can't come forward or backward. It can't go outside of the paper. So if the whole world is just this piece of paper, in some sense, it feels the world would be 2-dimensional because there are 2 independent directions. I show them with x-axis and y-axis. So this is a 2-dimensional world. We can have a 1-dimensional world too. Suppose we have just a line, and suppose there is a dot. Let's call it, let's give it a name. Let's call it Mr. Smith. This dot lives in that world. It can only go to right or left. There's just one direction. So this is a 1-dimensional space. So actually that's the key idea. We can have a 1-dimensional space, can have 2-dimensional space, we can have 3-dimensional space. So 1-dimensional space is just like a line. A 2-dimensional space is kind of like a plane. So 1-dimensional space is like a line, 2-dimensional space is like a plane. All the points on this plane. And 3-dimensional space is what we really call it space. It has 3 independent directions. So we call this 1-dimensional space. We show this direction with x. 2-dimensional space, we show these directions with x and y. And this 3-dimensional space, we show these directions with x, y, and z. Do we have the syllabus? Yes, we do. So I uploaded it on Blackboard. You can see it on the, so if you just search my name and Stony Brook and the name of the course, you would find the syllabus of the course too. And also I sent you a link, which I will send again, of the detailed schedule that in each specific day, I'm going to teach what specific topic. I would email everything one more time, okay? So this is a 3-dimensional space. And one natural thing to think about is that, do we have, for example, a 4-dimensional space? Is it possible to imagine a 4-dimensional space? Does anyone want to give an answer? Does anyone have an idea? So just look at the world around you. Time, that's amazing. That was fast. That is true. So 3-dimensional space, 3-dimensional space. It is 3D. We can have another dimension. We can think about time as the 4th dimension. Even if you sit, even if you don't move at all, if you don't go to right or left, if you don't move at all, there is another dimension which you are constantly moving forward in that dimension. And that's time. That is true. So we have 1-dimensional spaces, we have 2-dimensional spaces, we have 3-dimensional spaces, we have 4-dimensional spaces, but because time is slightly different with space, I mean in space you can You have freedom to go forward or backward. You have freedom to go right or left, up or down. But about the fourth dimension, the dimension of time, you don't have any freedom, right? You can't go back in time. You just go constantly forward. You can't even go faster or slower. In order to show these three-dimensional and the dimension of time, they are different, we usually write 3 + 1 dimensional space, which these three refer to space, and this one dimension refers to time. Okay, that's good. What about the higher dimensions? Do we have, can you think about a 5-dimensional space or space-time or something like that? First, tell me if this thing makes sense to you. I'm just speaking. This is not our rigorous math. I'm just talking now. But so this is a 4-dimensional. First of all, if you have any comment or if you feel something is not right, this is not really a 4-dimensional space, let's talk about that. Also, if you have any idea about what can be, if we can't even imagine a 5-dimensional space or space-time, I like to hear your comments on that too. Okay, feel free to unmute yourself and speak. Let's think about it as a discussion more than like me just teaching here, okay? Okay, so let me tell you the answer. So, spoiler, the answer is yes, we can have higher dimensions. There are slightly two different things. Gravity, you really think in terms of physics. That's good. Let's talk about that. Now, gravity is not a dimension itself. Gravity is something which appears in the framework of the space. So if we have 3 + 1 dimensional space, which is a space and time, gravity is something which in some sense exists there. It's not another dimension for itself. So first of all, in math, which is just something abstract, for a moment, let's assume math is independent of the real world. In math, we can have any dimension. We have 1-dimensional space, we have 2, 3, 4-dimensional space, 5-dimensional space. We have 100-dimensional spaces. We even have, in mathematics, we have infinite dimensional spaces. And they do exist in math. Something which might be even more strange for you is that in mathematics, we can have some spaces which their dimension is not even a whole number. We can have a space which its dimension is, say, 5/2. Okay, so we can have spaces with fractional or kind of as a rational number, with dimension as a rational number, or even irrational numbers. So we can have a lot of strange things in mathematics. But you might say, if they really appear in reality, in nature, is it possible to see these things in reality, or they just appear in math? So is tesseract a 4D space? Let me think, what do you mean by that? Yeah, in some sense. What Christopher says, yeah, that's kind of, that is true. And that's I think is a unit 4-dimensional cube. I would mention that later. Yeah, that's a good answer. So, but do these things, do these spaces, these higher dimensional spaces, appear in nature or reality? Okay, the answer is yes and no. Well, there are two ways to answer this thing. First of all, the answer is yes, because, you know, we never understand the world, the nature around us directly. We always, yeah, Dylan, that's the other answer. Thank you. The answer is always we model the nature. We kind of make mathematical models to understand the nature. So even if you are an engineering student, a lot of times when you are modeling something, the model itself has dimension. And it might be, the dimension might be above 3 and 4. I wouldn't go much into that now. That's something I would mention later. And the second answer, as Dylan mentioned here, is something called string theory. Physicists now think that actually the world is maybe something like 10 or 11 dimensional. What does that mean? So when you look around yourself, you feel you're living inside a three-dimensional space. And we said because there is also time, we think about time also as one extra dimension. So 3 plus 1 is 4. But some physicists tell us, actually we are living inside a 10, for example, 10-dimensional space. So what are the other dimensions? Why we don't see them? If there are extra dimensions, we should be able to feel them, right? The answer is in some sense like this. If you look at a piece of paper, it looks like two-dimensional, right? You can go to right or left, you can go up or down. So a piece of paper looks like it's two-dimensional. But in reality, it's three-dimensional, right? Because if you look very, very carefully, if you have a magnifier, if you put it here, the piece of paper you would see would look like this. This is the piece of paper, but it also has a third dimension. If you look very carefully, right? That's what you would see. It is actually three-dimensional. Or if you just look at your hair, it looks like a line. But if you look at that with a magnifier, you would see it's not just a line. It looks like this. It's a three-dimensional thing. But actually, because that second or third dimension is very small, we don't see that. That's also apparently the case about our world. There is a three-dimensional space, there's one-dimension time. There is another six-dimensional space, but those dimensions are so small that we don't feel them. They're very, very, very tiny. So let me write it here. Very, very, very tiny. So that's why we don't feel them. But for example, if we are here, we are in three-dimensional space, we don't see those extra dimensions, but those dimensions exist and they really affect our world. They really have a meaningful existence. They change things. They change the way the world behaves. So although they are small, but they are important. Okay, so that's the other answer. So these dimensions, they do exist. And multivariable calculus, we try to understand the higher dimensions, and we like to do math in higher dimensions. So one-dimensional mathematics is one-dimensional math is just things you've seen in Calc 1, Calc 2, or calc A, B, C, or things like that. We have the real numbers. We show the set of real numbers, probably all the numbers you know, with R. It has 0, it has 1, 2, 3, -1, -2, -3, and everything in between, like 1/2, square root of 2. All these numbers are here. And it looks like a line. So it's a one-dimensional space. And in the previous courses, like in Calc 1 and 2, you were thinking about functions from R to R, right? For example, y equals x squared. It's a function which its input, x is the input, is a real number, and the output is x squared that's also a real number. So we can think about this function as a, so f here is a function from a one-dimensional space, which is R, to another one-dimensional space. And then whenever we have these functions, we can take limits, we can take derivative, we can take integral, and all these things. What we want to do in this course is we want to look at functions from where the domain rather than R is R to the n. R to the n means n-dimensional space. The higher dimensional space. And the range is also some other m-dimensional space. And we want to study these functions. We want to see if we can take limit, if we can take derivative, if we can take integral. So we want to be able to work in these higher dimensions. That's the idea. Okay, any question up to this point?
Are n and m always going to be the same?
No, they can be different. That's why I use different letters, because, yeah, for example, we can have a function f from R2 to R. It means a function R2 is R times R. R2 means two-dimensional space. R is one-dimensional space. So it's a function from two-dimensional space to one-dimensional space. I will talk about these things. Now I'm just giving an overview of the course. Okay, so we need to understand these dimensions, these higher dimensional spaces better. Let's start with two-dimensional space. Two-dimensional space means plane, just like a piece of paper, right? We use coordinates to kind of show the numbers, show the points on a piece of paper, on a plane. So maybe one thing to say before going there. If you look at the world around you, like geometry, in physics, in chemistry, in a lot of different places, we have quantities, right? There are a lot of quantities that every day we think about them, we work with them. Most of the time, we can present these quantities with numbers, like, for example, the temperature. We just need a number to say what is the temperature, right? Like time, like mass, right? Like area, like volume, like length. These are quantities which these quantities, the important thing about them is that we can measure them and we can express them in terms of just a single number. Okay, these quantities are called scalar quantities. But all quantities are not like that. We have other quantities which just one number is not enough to completely understand them. So, for example, so other kind of quantities. For example, suppose we have the Earth. In this course, you are assuming Earth is not flat, right? It's more or less looks like a sphere. We have the Earth, and we are living somewhere on the Earth. So the position, it's a quantity. Where do you live? We can use numbers like longitude and latitude to say where we live. So just one number is not enough. There is no way that we can express where we are in a good way with one number. We need more than one number. That's one example. Or another example, in physics, we have force. Force, well, if you are not familiar with that, in physics, for example, let's say this is the ground, there is a box here. Okay, you're trying to push that box. So when you're pushing a box, it not only matters how much force you're using, also there is another thing which matters, is the direction of the force. The unit of the force is Newton. So for example, let's say we are pushing this box with 5 Newton. If you're pushing it that way, it's completely different with the case where you're pushing the device in the opposite direction. In both cases, the force is 5 Newton, but the direction matters. And also, so if you push it from left to right, the box would go that way. If you push it from right to left, the box would go the other way. If you have the same box and if you push it in this direction from above to below with the same amount of force, the box wouldn't move. So not just a number, here 5 is a number, but that's not everything. We need something more. We need direction. So there are quantities which, in order to understand them, we need a number plus a direction. So force is one example. In physics, speed is another example. So you might say, no, when I'm driving, if someone asks me how fast I'm driving, I can answer with just one number, right? But that's slightly different in physics. It's slightly different from the way we speak in like everyday life. In physics, so for example, suppose this is a map and you're driving, and suppose you're here and you're driving and you have a certain amount of speed. Let's show it with X. Okay, suppose this is your speed. It's not enough to say it, to present it as a number. You also need a direction. But so when we say speed in physics, we mean a number, but also a direction. So for example, in which way you're driving? Are you driving that way? Are you driving this way? So we need also a direction. That's another example. So for example, well, I mean, it's different in different systems, but I prefer to use SI unit. So in SI, the unit of speed is meter, or it's actually correct to write it as like that, per second. So for example, if the speed is, I don't know, 10 meter per second. Yeah, that's kind of, okay, that's slightly different in the, you know, yeah, you're kind of correct. Maybe it's better to use velocity rather than speed. Thank you. I also prefer to say velocity. I thought maybe speed is more, yeah, probably you're right. Let's use velocity. So a number is not enough to say what's the velocity, but also a direction. Yeah, thank you. We have other similar things too. For example, acceleration. That's another example. Do you have any other example in mind of these quantities which you don't only need, well, a number is not enough, you also need to kind of, you need additional thing. Yeah, Jarek, these things are correct, but no one uses them anymore. I mean, that's correct. Displacement is good. Jerk is the change of acceleration, right? Displacement is also correct. So if I just tell you the amount of displacement is 5 meters, that's not enough to understand. So if I tell you we had an object, okay, we should go to the first one. Let's clear the space. So if we have an object here, at this point, object A, if I tell you displacement is, say, 5 meters, you wouldn't understand where the A would be. I should tell you the direction. If I tell you that's the direction, and then after 5 meters, you know A would come here. Magnetic field, yeah, those are exactly, those are more, magnetic field is certainly a correct answer. I didn't mention that because they are not even vector. Although we might think about magnetic field as a vector in beginning, but very soon we would understand those are in reality what we call them as tensors. And tensors are more complicated. I wouldn't get to them right now, but kind of at the end of the course, we would understand these things better. We would understand that if we want to think about magnetic field or gravity or Maxwell's equations, or I don't know, Einstein approach to geometry, how we can even think about those quantities correctly. Okay, so let me clear my drawing. So what we understand now is that the quantities, some of them, we can express them just with a number. We call them scalar quantities. We just need to use a single number. Some quantities are slightly more complicated. Just a number is not enough. They are kind of what we call them a vector. We need a number plus a direction. And also there are more kind of complicated form of quantities. Magnetic field is an example. We call them tensor. I don't talk about them now. At some point we might mention them. So magnetic field, or things in the sense of gravity or curvature of space-time, or things are of that example, but let's keep that for later. Okay, so any question? Any comments? Is the quality of my voice good for everyone? Is there any problem with internet or anything? Okay, I assume everything's good. Okay, so let's start to think about vectors. So let's start to think about vectors first in two-dimensional space. Two-dimensional space, well, because it has, I would later make it more clear what I mean, but in some sense it has two independent directions. One direction is the direction of X, the other direction is the direction of Y. Any other direction is in some sense something in between, right? That's not independent. Anything else is kind of a combination of X and Y. So two-dimensional space has two independent direction, X and Y, right? Now, any point, say P here, because I think we also have high school students, maybe I should be more careful and mention all the details. So any point here, it's P is just a point. I can express where P is using two numbers. So I can take a unit on the X direction. I would have 1, 2, 3, 4, etc. And -1 in the other direction. And then on the Y direction, I have 1, 2, 3, 4, etc. And the negative numbers are in the other direction. Now, any number, any point P in this space, I can express where it is using two numbers, which are called coordinates of P. So first I should look, so this is a point P, I should look at this x-axis. If I project P down on this x-axis, I would see this number 2. So the first coordinate of P is 2. And then there is a second coordinate. I should look at this y-axis and I see 3. So I present this point P with 2 and 3. These are coordinates of P. So let's look at another example. Let's try to find Q with coordinates 4 and 1. So the first one refers to x-axis, 1. So when I'm saying 4 and 1, I should look at these. The first one is x-axis. I should look at these ones, 1, 2, 3, 4. This is 4. And then the second coordinate is the y-axis. 1 is here. So I should have a point which is, its x-axis is 4 and its y-axis is 1. The intersection of these two lines is this point Q. So if you look at the x-axis, you would see 4. If you look at the y-axis, you would see 1. So that's the way to use numbers to show points on the plane. Okay. So let's go back to the plane, X and Y. So sometimes I might not write down these numbers on these axes. It really doesn't matter. I'm doing that now, but later I might not do that anymore. Okay, now if I have 2 points, say P and Q, there are 2 points here on the plane, I can connect them with a vector. So suppose I have a vector connecting P to Q. Just to fix a notation, I would use PQ with small vector above it to present this vector which connects P to Q. So that's just my notation. And if I have the coordinates for P, well, in this case, P is 2 and 2. And Q is 4 and 4. This vector which connects P to Q is equal to Q minus P. That's the important thing. Q minus P means you start from P and you end up at Q. So this PQ in this case is Q, which if you look, Q is 4 and 4. And P is 2 and 2, so 4 and 4 minus 2 and 2. The result is 4 minus 2, which is 2, and 4 minus 2, which is 2. So this vector P and Q is, in this case, is equal to 2 and 2. That's the way to work with vectors. Okay. So maybe let's look at just one more example to make sure we are all on the same page. So suppose we have this plane. Again, here we have P, and say here we have Q. So where is P? Minus 1, minus 2. So the first coordinate of P is minus 2. The second coordinate of P is 1, 2, it's 2. So the coordinates of P are minus 2 and 2. Where is Q? The first coordinate of Q is 2, and its second coordinate is minus 1. So if I look at PQ, the vector connecting P to Q, it's supposed to be Q minus P, which means minus 2 and 2, that's Q, minus, I'm sorry, Q is 2 and minus 1, minus P, P is minus 2 and 2. So the first coordinate would be 2 minus 2. And the second coordinate is minus 1, minus 2. Which the result is 2 minus minus 2 is 2 plus 2, which is 4. And minus 1 minus 2 is minus 3. So PQ is equal to 4 and minus 3. Okay, any question here? Is it clear how we are defining vectors and points and how we find coordinates of points and coordinates of vectors? Yes, that is true. Well, that was the second thing I wanted to talk about. Yeah, so when we have a vector, this vector is connecting one point to another. So I have 2 points here, P and Q. I will connect them with the vector PQ, which is this vector here. And it has 2 coordinates. Each of these coordinates is called a component. The first one is called the X component. And the second one is called the Y component. Also about the points. So for example, if P is a point here, say this is, maybe it's better to make them different. So 1, 2, 3, 1, 2. So the first component of P is 3, first, or the X component. We sometimes say the X component, sometimes we say the first component is 3. The second component of P is, the second component of P, or the Y component of P is 2. So we also sometimes we call it the second component. So actually that's the real meaning of dimension. If I have a point P here, if I want to tell you where is P, I need 2 numbers to tell you where P is, right? The first one, 3, the second one, 2. I need 2 numbers. If in a space you need two numbers to tell me where P is, it means that space is two-dimensional. For example, think about the surface of the Earth, right? It's almost a sphere. In order to tell me where are you, for example, you can tell me where is your longitude and latitude. So you need two numbers to tell me where you are. And so two numbers. So when you want to express your coordinates, you need two numbers. So the surface of the Earth is two-dimensional, although it's not flat. So a piece of paper is two-dimensional, but it's flat. The Earth is not flat, but it is still two-dimensional space. But for example, if you want to tell me the coordinates of another star in another galaxy, if you want to tell me its coordinates, two numbers wouldn't be enough. Actually, we'll need at least three numbers. And it shows, at least in our model, we think about the universe, the world around us, as a three-dimensional space, right? So in some sense, the numbers you're using to describe the location of every point is the dimension of the space. Okay. Okay, so we have vectors. We have vectors in plane, vectors in plane, and we use coordinates to express them and show them the locations and things like that. Okay, so that's the first thing to understand. We can do the same thing in higher dimensional spaces. I will do that, but before doing that, there's another thing I want to discuss, and that's length of a vector. So if I have 2 points, P and Q, I can use a vector to connect them. I want to see what is the length of that vector. In some sense, and that's the notation I will use. This notation means the length of the vector. So in some sense, if I have an object here at P, if I move it to Q, the length of PQ is the displacement, is how much I've moved this object, right? So for example, suppose the point P, the coordinates of P are 2 and 2. The coordinates of Q are 6 and 1, 2, 3, 4. So suppose P, the coordinates of P are 2 and 2, and the coordinates of Q are 6 and 4. So this vector PQ is equal to 6 and 4 minus 2 and 2. 6 minus 2 is 4, 4 minus 2 is 2. Now I want to compute the length of this thing. I want to compute the length of 4 and 2. What is the length? Okay, how can I compute the length? That's the question. Okay, does anyone know how I can do that? That is true. I can use Pythagorean Theorem. That is true. Yeah, that is true. Pythagorean, distance formula. Pythagorean Theorem. So let's just remember, what does the Pythagorean theorem say? It says if you have a right triangle, remember it has to be right triangle. Here the angle is 90 degrees, or pi over 2. If the length of this side is C, the length of this side is A, and the length of this side is B, the Pythagorean theorem says C squared is equal to A squared plus B squared, right? Now, we can use this. We can use this to compute the length of a vector. So again, let's go back. We had P here, 2 and 2. We had Q here, 6 and 4. We connected them. Now we can construct a triangle here. We can add these two sides to get a right triangle. What is the length of this side? Well, it's easy because this point here is 2, this point here is 6, therefore this length is 4. Therefore, this length here of the triangle has to be 4. What about the other side? The coordinates of Q are 2 and 4. This length is equal to this red length, but it goes from 2 to 4. So the length is 4 minus 2, which is 2. So this length is 2. So we have a triangle which one side is 4, the other side is 2. And we want to find C. Pythagorean theorem says C squared is equal to A squared. Say this is A, this is B. So it's going to be 2 squared plus 4 squared, which is 20. It means C squared is 20. C is square root of 20. Okay. Okay, now it's now we can have a 15-minute break. We can continue at 11:20. Is there any question? I mean, it's a good time now to ask me if you have any question.
It's a 10:05, not 11:05.
Oh, you're right. Sorry, it's the first time I'm teaching. Okay, do you want to have, maybe it's good to have a 5-minute break actually. So not 15-minute break, it would be a lot. But let's have 5-minute break because I also need to break the recorded videos into smaller pieces. So let me stop recording.